All right, let's dive in. Today we're looking at a really extreme exoplanet called WASP P121b.
Yeah, this one's pretty wild. An ultra-hot giant.
And we've got some great new insights thanks to the James Webb Space Telescope, right? Data from a team led by Thomas Evans Soma and Cyril Gap.
Exactly. They've managed to get this amazing chemical fingerprint of its atmosphere.
A chemical fingerprint, okay.
And that's really our mission for this deep dive. Figuring out what that fingerprint, these specific molecules they detected, tells us about where WASP P121b came from, how it, grew up.
So it's like planetary archaeology using chemistry. What's the power of looking for these specific molecules? Why does that tell us so much?
What's huge, these molecules, they act like probes. They tell you about the chemistry, the temperature, even how things are moving around in the atmosphere.
And JWST is the tool for the job here.
Oh, definitely. It's near-infrared spectrograph, and our spec is just fantastic for this kind of work. It can sniff out these molecular signatures.
So what did the team actually find? What were the key molecules?
Well, there's water vapor, H2O. That's pretty standard. Gives you a handle on the oxygen.
Okay, oxygen check.
And carbon monoxide, CO. Really robust indicator for carbon. Put those together, and you start getting at that crucial carbon to oxygen ratio, the CO ratio.
Right, the CO ratio. We'll probably come back to that. But I saw something else mentioned that seems unusual for an atmosphere. Silicon monoxide, SEO.
Yes. And that is fascinating. Silicon, and it's usually locked up in rocks, silicates.
Yeah.
Finding it as a gas, FAO, that tells you it's unbelievably hot there.
Hot enough to vaporize rock, literally.
Pretty much, yeah.
Yeah.
Hot enough that materials we think of as solid are just floating around as gas.
Wow, okay. Any other surprises?
There was one more that really makes you think. Methane. CH.
Methane, hang on. Isn't methane more of a cold planet thing like Jupiter or Saturn way out there?
Exactly. That's the puzzle. Finding it on a planet this scorching hot. It doesn't immediately make sense if you just look at the average temperature.
So what does it mean then?
It strongly suggests there's some serious mixing going on. Even if methane can only really survive on the cooler parts, something powerful must be churning the atmosphere and bringing it into regions where it really shouldn't last long.
Okay, so we have this inventory, water, CO, this vaporized rock stuff, SiO, and methane, hinting at major atmospheric churning. And the next step is comparing this planet's chemistry to its star.
Precisely. The star's composition is like the starting recipe for the system. If the planet's different, especially in key ratios like CO, it tells you something important happened during its formation.
Before we get to the formation story, let's just picture this planet. You said ultra hot. How extreme are we talking?
We're talking really extreme. It's a gas giant,
Yeah.
bigger than Jupiter, and it orbits incredibly close to its star. Like, the gap between them is only about twice the star's own diameter.
That's basically skimming the star's surface, almost.
Yeah, it's incredibly close, which means its year is super short.
How short?
It's about 30.5 hours to go all the way around.
30 hours for a year. Okay, ultra hot definitely fits. And orbiting that close, it must have crazy temperature differences.
Oh, absolutely. It's tidally locked, so one side always faces the star. Perpetual day.
Like our moon.
Exactly. And that day side gets blasted. Temperatures are over 3,000 degrees Celsius.
3000 C. Okay, that explains the vaporized rock, the SiO.
Right. Hotter than the melting point of most rocks. Then you have the night side, always in shadow.
Is it actually cool there?
Well, cool is relative. It's still around 1,500 degrees Celsius, so incredibly hot. It's just less incredibly hot than the day side.
1500 degrees, still brutal, but maybe cool enough for methane? Is that where it ties in?
That's the idea. 1,500 C might be just cool enough for methane to hang around, but finding it suggests it's not just staying put on the night side.
Right, because of the mixing you mentioned.
Exactly. It implies these really powerful vertical winds, almost like storms, are dredging methane up from deeper, cooler layers or from the night side and mixing it around even into hotter areas where it should break down.
And this kind of intense mixing, that's pushing the boundaries of our atmospheric models for these planets.
It definitely is. It suggests these atmospheres might be even more dynamic and complex than we thought.
So we've got this picture. Scorching day side, boiling night side, vaporized rock, and methane being whipped around by intense winds. How does this chemical cocktail, this fingerprint, tell us where WASP-21b was born?
Okay, this is where that carbon-to-oxygen ratio, the CO ratio, becomes super important.
Right, you mentioned that earlier.
The relative amounts of carbon versus oxygen that a forming giant planet gobbles up from the gas disk around its young star. That depends a lot on where in the disk it forms, specifically the temperature there.
Okay, and what did the team find for WASPN 121b's ratio compared to its star?
They found it has a significantly higher CO ratio than the star itself.
Higher carbon to oxygen. What does that imply about its birthplace?
Well, think about the disk around the young star. Close in, it's hot, everything's gas. Further out, it gets colder. First, water vapor freezes into ice. That's the water-ice line. Go even further out, and it gets cold enough for the methane gas to freeze into methane ice. That's the methane ice line.
Two different freezing points.
Exactly. Now, if a planet forms between those two lines.
So water is already frozen, locked up in ice pebbles.
Right. So the gas the planet accretes is low in oxygen because the oxygen is mostly in that water ice.
But methane is still a gas in that zone?
Precisely. So the gas is relatively enriched in carbon. A planet forming there will naturally end up with a higher CO ratio than the original mix from the star.
And that region between the water and methane ice lines, where would that be, roughly?
The paper suggests that in our own solar system, conditions like that were somewhere out between Jupiter's orbit and Uranus's orbit, much further out.
So the high CO ratio is basically a signpost saying, I was born way out here in the cold.
That's the strong interpretation, yes.
Yeah.
It suggests WSP 121b formed far from its star and then somehow migrated all the way into its current scorching orbit.
That's quite a journey. But it wasn't just about collecting gas, right? The source mentions solids and eventful youth. How does the silicon monoxide, the SiO, fit into that part of the story?
Good point. Planet formation isn't just gas. You need a core first. That starts with tiny dust grains sticking together, growing into pebbles, maybe centimeter or meter size.
Made of rock and ice out there?
Yeah. And these pebbles, they feel a drag from the gas in the disk, causing them to spiral inwards.
Like air resistance, sort of?
Kind of, yeah, aerodynamic drag. As they drift closer to the star, any ices they contain can evaporate. The growing planet sweeps up these pebbles and the gas.
Okay. Standard planet growth.
But then there's another type of solid body, planetesimals.
Yeah.
These are much bigger. Think asteroid size up to moon size, mostly rocky.
And silicon comes mainly from rock.
Exactly. Forming these larger planetesimals takes more time than just growing pebbles. So if the silicon, which we see as gaseous SiO now, came from accreting these rocky planetesimals.
That suggests the rocky stuff arrived later in the process.
That's the inference, yeah. It implies WATS-P 121b probably gathered most of its huge gas envelope first, out in that cold, carbon-rich zone. Then, later in its development, it accreted a significant amount of rocky material via these planetesimals.
Wow. Okay, so the story gets richer. Form the core far out, grab lots of carbon-heavy gas, then get bombarded by or merge with rocky planetesimals, and then undertake this massive inward migration.
It paints a picture of a really dynamic multi-stage formation history, not just a simple, steady accumulation.
And that leads to the question the researchers ask, right? Is this complicated path common for hot Jupiters, or is WASP 121b something special?
Exactly. We need to study more of them like this to know for sure.
So how did JWST actually manage to get all this detail? You mentioned NRSpec, but what were the specific techniques?
They used a couple of clever methods observing the planet over its entire 30.5-hour orbit. First, phase-resolved emission spectra.
Okay, what's that?
Basically, you watch the planet as it orbits and measure the infrared light, the heat coming directly from it. As different parts rotate into view, the super hot day side, the cooler night side, you can map the temperatures across the planet. That's how they got the day-night temperature difference and probed the night side.
Seeing its heat signature change as it turns makes sense. What was the other method?
Transmission spectra.
Right.
This happens when the planet passes directly in front of its star, from our point of view.
A transit.
Right. During the transit, a tiny fraction of the starlight filters through the planet's atmosphere right at the edge, the terminator region where day meets night.
Like looking through the atmosphere's thin outer layer?
Exactly. By analyzing which specific colors or wavelengths of starlight are absorbed or blocked by that atmosphere, you can tell which molecules are present there.
And putting those two together, the direct heat map and the filtered starlight that confirmed the SiO, CO, and HO.
Yes, combining the data from both methods gave them really robust detections of those molecules.
But you mentioned methane was a bit different. It wasn't seen everywhere.
That's right. The methane showed up in the emission data, suggesting it's present, likely more stable on the night side. But it didn't show up in the transmission spectra, the data from the terminator.
Why would it be missing right at the edge, the transition zone?
Well, the hypothesis put forward in the paper is tied to that intense mixing and the extreme temperatures. As those strong winds carry methane from the cooler night side around towards the incredibly hot day side, it has to pass through that terminator region. And the thinking is, in that transition zone, the combination of increasing heat and maybe direct starlight is just too much for the methane. The molecules get rapidly broken apart,
Destroyed before they can even make it fully around to the day side, or at least right at that boundary.
either through photodissociation being broken by light or just thermal decomposition being torn apart by the heat.
Okay, that's a fascinating level of detail. So, bringing this all together, why does delving so deep into this one, frankly terrifying planet matter for us? What's the bigger picture?
Because this detailed atmospheric breakdown, thanks to JWST, it tells a story, a really compelling one. It's a narrative of a planet born far away, getting a late snack of rocks, and then going on this dramatic inward spiral.
It really drives home how powerful this type of spectroscopy is becoming. We're not just finding dots of light anymore, we're starting to read planetary biographies.
Absolutely. We're moving beyond just cataloging planets to actually understanding the often quite violent and complex physics and chemistry that shaped them.
And for you listening, by digging into the specifics of WASP-121b's seemingly unique history, formed carbon-rich, far-out, added rocks later, migrated inwards, we get these aha moments. It sheds light on the whole messy, amazing process of how planets form everywhere.
It really challenges some of the simpler models we might have had about how giant planets form and end up where they are.
It suggests the universe has a lot more ways to build planets than we might have assumed. It's not just about this one world, but about appreciating the incredible diversity out there.
Exactly. It shows the sheer variety of outcomes possible.
It really makes you wonder, given those powerful vertical winds needed to explain the methane, what other secrets might be hiding just below the observable layers in these ultra-hot atmospheres? What dynamics are we not quite seeing yet?
Or flipping it around. How common is this specific formation pathway? The carbon-rich gas first, then the rocky planetesimals, then the big migration. Is WISP-121b an outlier, or is this a frequent way how Jupiters come to be? We just don't know yet.
It really leaves you thinking about how many different, maybe equally wild stories are playing out on planets across the galaxy. Just how unique was WASP-121b's chaotic journey?